In this video, we're going to reinforce the ideas we introduced earlier around the matrices of linear transformations. We're going to do another practice exercise where we have a mapping from R3 to, if we look carefully here, R2. We have one element here as the output and then a second element. So there's only two output values. Again, if it helps, we're mapping from R3 to R2 over here. And that L is bridging the gap between those two spaces. So in terms of the matrix that we're going to build for this transform, how big should it be? Again, the number of rows is equal to the number of outputs, which in this case here is 2. And the number of columns is equal to the number of inputs, which here is 3. So we have 3 inputs and 2 outputs. These define the scale of our matrix. So it's going to be 2 rows by 3 columns. And again, looking at some earlier examples, we can take a bit of a shortcut now. We could think through the whole 1, 0, 0, 0, 1, 0. We know if we set x equal to 1 and compute the output, that should give us the values for the first column. But we also know that those are just the coefficients of x. So we can just read the coefficients off as a bit of a shortcut. When I plug 1 in here, I'm going to get -2, 11. So the coefficients are really defining what the output is. So I can go straight away to -2, 11. Then we can repeat that for y, which has coefficients -4 and 15. And then we can repeat that again for z one last time, 3 and 8. Then we could verify if we liked. For example, this transform here, if we took the transform of 0, 1, 0 and did the work with the function up here, we would absolutely get the values -4 and 15. All right, so what other shortcuts or rules of thumb should we be aware of as we're doing this? Well, for example, we should be able to quickly identify the size of a standard matrix if we know the input and the output. And that requires remembering that the number of rows is equal to the number of outputs. Or if you like, another way to remember that is that each column is equal to an output vector, just put vertically. So if you have a column and you want to know, well, how many ingredients are in there, that's going to be the number of outputs we have. So here we have 5 output variables, 5 output dimensions. And so the number of rows, which is the first thing in a matrix, is going to be 5. Then if we look at how many of those columns there are, there's 1 column for each input. And because we have 7 inputs, we're going to have 7 columns for that. So whatever mnemonic you want to try to keep, totally fine. But at the end of the day, if we're mapping these functions, one way to simply memorize it is the input dimension is the number of columns and the output dimension is the number of rows. And we usually list rows before columns. Sorry, we don't usually. We always list the number of rows by columns as the matrix dimension. So quick check for this. Try it yourself for a moment. If we know that a matrix is 6 by 8, so we put the matrix on here, it's 6 rows by 8 columns. What are the input and output dimensions for this? We're going to go from R to R, take a moment to think about it, if you want to pause, and then we'll put it in. So 6 is the number of output dimensions. So we're going to have columns that are in R6, and then we're going to have 1 column for every input, so we must have had 8 inputs to start with. And that just gives us a quick idea of, if we're given a matrix, what can we learn immediately about the scale of the inputs and the outputs of that kind of linear transform.